Finally, we're ready to go. Thanks, Ruth. Yeah, so I'm from the University of Tennessee at Knoxville, and I'd like to present some performance analysis tools from academia, which are designed for performance analysis for the multicore area, more or less. So I'm going to be biased. I'm going to focus mostly on tools which I am involved in some way, and in particular, I'm going to focus very much on a profiling tool for OpenMP, where I've been involved. So that's the outline of the talk. I'm going to first have a slide on the performance tools world, the separation between the tools from the commercial tools and the tools from academia. Then I'm going to have a pretty big part on performance analysis with this OpenMP profiling tool, which is called OMPP. I'm going to talk about its features for overhead analysis and scalability analysis, and some interesting technique which tries to combine the benefits of tracing and profiling. And then I basically have one slide on a couple of other tools, and those tools some of you might be familiar with are PAPI, the Tau tools, Vampire, KOJAK, and SCALASCA, which are tracing tools. And there is one slide on tool operability, which is, I think, a big bonus of the tools from academia. Basically, all those tools work together in some way. So the performance tools world, there are, of course, the vendor tools. Marty just talked about the Sun Studio tools. Then Intel has a range of tools as well, the thread profiler, the thread checker, the thread analyzer, vTune. Cray has its set of tools. And those tools are very powerful, and they have the advantage of being commercially supported. So you usually get a lot of support with your problems, and you basically have a guarantee that they work on the platform. But of course, then the disadvantage of those tools is that they are usually limited to the vendor's platform. Now, Linux is now prevalent on many HPC platforms, but still, you probably won't get the Sun tools to work on an IBM system with AIX, for example. The tools from academia, on the other hand, have the advantage that they're usually designed to work on pretty much any platform. Those tools from academia, which you're probably most familiar are, is PAPI. It's a tool or a tool set for accessing hardware performance counter data. Tau from the University of Oregon is pretty much the Swiss Army knife of tools. It works pretty much anywhere, and it does anything. It does tracing, profiling, call path profiling, all kinds of stuff. KOJAK and SCALASCA are an interesting tool set which tries to automate the process of performance analysis. So it captures traces, but it really tries to condense the information which is contained in the traces into a more easily understandable format. Vampire is a trace visualization tool which is widely used, and OMPP is the profiling tool, which I'm going to cover in more detail now. So OpenMP is one of the containing programming paradigms for Multicore. OpenMP works, as many of you know, in a fork and join-based manner. You start with a master thread that forks off into parallel sections. And in the parallel sections, you actually do employ work-sharing constructs to get and speed up over a sequential execution. The characteristics are that it's based on directives. It allows for an incremental parallelization approach. It has been discovered that it's very well suited for loop-based parallel programming until now. Until now, it was a little bit less well suited for more irregular forms of parallelism. And that's going to change, though, with the upcoming version 3 of the standard, which is going to include a tasking construct, which will allow for a much more dynamic way in which to express parallelism. And it's, of course, one of the containing programming paradigms for the so-called multicore area. And I think it's a pretty good candidate to be successful in that respect. So OpenMP Performance Analysis with OMPP. OMPP is a profiling tool for OpenMP. It's been developed at the University of Tennessee and in Munich. In contrast to the tools by Sun, it's based on source code instrumentation. So that has the disadvantage that the user has the burden of additional step before he can run his application with the tool. but it has the big advantage that it's basically, it makes the tool independent of any compiler or OpenMP runtime system. So the way in which it works is you take your source code, you run it through an instrumentation stage, which automatically instruments OpenMP constructs. In addition, you can manually instrument regions of interest for you. So you might mark regions like initialization or phases of your program. You might mark the outermost loop manually. Then you have your executable. You run your executable, and some settings take effect. And in the end, you get a profiling report. When the program finishes, you get a profiling report of the program run of your application. So that's an example of how the profiling data looks like in OMPP, yes. So that's a very simple OpenMP code fragment. You have a parallel region and a critical section inside, and you just have a sleep construct there. And so the profiling data here is based on an execution with 4 threads. So you have thread ID 0 to 3. And the thing to notice here is simply there are a number of different columns here, each specifying different aspects of that critical region. So for example, you have the exec t is the total execution time of the construct, while body t is the time which is spent inside the body of the construct. So there's 1 second in each case here. And the enter t here is the time which each thread had to wait to enter the critical section. So a critical section means each thread can only enter the body of the critical section after another one has exited it. And so you get this kind of data for each type of OpenMP construct by using this profiling report. And so what you can also do is you can also specify hardware performance counters. So in this case, the user has selected to measure the total instructions, and it has selected the counter PAPI total instructions, and you see those counter values here as additional columns. So based on the data which is delivered by OMPP, you can do an overhead analysis. So because certain timings which are reported by OMPP can be classified as overheads. So for example, as we saw in the earlier example, the enter time, the time required to enter a critical section can be regarded as a synchronization overhead. And based on that observation, there are 4 categories defined in OMPP. Those are imbalance, that's the waiting time incurred due to an imbalanced amount of work. Synchronization, that's the overhead that arises because threads have to synchronize their activity. Limited parallelism arises when threads do not have enough work, not enough parallelism is exposed to the amount of threads that are available. And thread management overhead, which is the overhead which is related to the creation and destruction of threads by the runtime system. So here is a chart that on the left-hand side gives all OpenMP constructs, and the top here shows the different timings and counts which are reported by OMPP. And so basically you have a dot if the particular time and count is reported. And the things which are colored here can be considered as overheads. So for example, the time required to enter a critical section is considered a synchronization overhead. For locks, the same time means the time to acquire a lock. The same things holds true for the time to enter a barrier, for example. And so based on that chart, you can do a classification of the times to vary to those 4 overhead classes. The overhead report, which is delivered by OMPP, looks like that. Basically, you get, for each source code region which you have here in your program, you get a breakdown of the total execution time into useful work and those 4 overhead categories, so synchronization, imbalance, limited parallelism, and management. And based on that data which is delivered by the overhead analysis report, you can do quite interesting scalability analysis. So all examples which I'm going to show here are from the spec OpenMP benchmark suites in the medium size, and scaling from 2 to most of the time to 32 threads on an SGI Altix machine. And so that example is from the application 314M grid. And what you see here is the breakdown of time, total execution time towards the useful work, and various overhead classes. So the biggest overhead which you see here is imbalance. And as it turns out, a phenomenon which you can identify here is that for powers of 2, like 16, or for 32, you have a markedly smaller imbalance overhead here in this application. And so if you analyze this phenomenon more closely, you see that that actually happens only for 3 parallel loops in the application. And if you look at the iteration count of those loops, you see that they are always a power of 2. And hence, if you have a power of 2 thread count, those divides evenly, and you don't have an imbalance, while in other cases you have a higher imbalance. So here's another example of that scalability analysis. That's the application 316 app blue. What you see here is a superlinear speedup. So in a perfectly scaling code, what you see here is always the summed execution time over all threads. So perfectly scaling code would be a horizontal line. So in this case, you see here a superlinear speedup. And again, if you analyze the data more closely, you see that it's actually only one parallel region which shows that superlinear speedup. And to investigate more closely, in this case, I've tried to analyze the L3 misses, and sure enough, it turns out that that's the most likely cause for the superlinear speedup. As for 2 and 4 threads, you have quite high number of L3 misses, and for 8 threads, the data set fits into the combined cache, and the L3 misses go down, which most likely explains that superlinear speedup here. So another interesting thing is incremental profiling. With incremental profiling, the idea is to try to combine the merits of profiling and tracing. And that's implemented in OpenMP by simply capturing profiling reports not only at the program end, but by capturing it in regular intervals. And what you can do by that is you can look at how the overhead behaves over time. So here's another example from the OpenMP spec benchmarks. What you see here is that you have a huge spike of synchronization overhead over the execution time. Again, if you investigate that more closely, you see that you basically have an initialization code in a critical section that effectively serializes the execution for approximately 15 seconds. So at the beginning of your calculation, you have a huge synchronization overhead here. Other things you can do is with incremental profiling is you can try to see on the x-axis here you have time. Each tile basically represents 1 second, and on the y-axis you have the number of threads. What you can see is how the hardware counter data behaves over time, more or less. So what you see here is it looks like iterative behavior. You have always phases that seem to repeat, and you also have some sort of thread grouping. You always see pairs of 2 threads that seem to behave similar. I've not yet investigated what the reason for this is in Multicore. Another example from the spec OpenMP benchmarks, again, this time the counter is floating point operations retired. Here you see a very different behavior of threads 0 to 14 versus 15 to 31. Again, I've not investigated in detail what the difference here is, but it seems to be a very interesting thing to look into more closely. So I should at least cover the other tools also a little bit. So PAPI is a monitoring tool for hardware performance counter. It tries to define a common set of counters for over a wide range of platforms, but it also gives you always access to all the counters which are available on any platform. Now, some recent new developments which are very exciting are that you can actually, it's called component PAPI. PAPI supports multiple measurement of multiple components at the same time. So not only does it support the CPU counters, it also supports counters on network interface cards and things like temperature sensors which are on the main board. So here you see an example that's a number of iterations of an application. And so down here you see the packets which get in and out. The red line here is the temperature which was measured, and the blue stuff here is the floating point rate in megaflops. So that's quite interesting to correlate all the different counters into one big picture. Tau, of course, it is a very big and integrated tool set. It supports OpenMP, MPI, and Java, and many other programming approaches. A very interesting feature of Tau is Paraprof. It's an interactive view of performance data. It supports 3D visualization of your performance data. And it can also import many other profiling and formats. Vampire is a tool for visualizing traces of mostly MPI applications. It supports many statistical views of your messaging activity. It also supports PAPI. So down here you see actually the counter activity over the timeline also. KOJAK and SCALASCA are two tools which try to automate the process of performance analysis. They trace the application and then perform an automated search for patterns of inefficient execution. So the idea is take the big data, big amount of trace data, try to combine it in an automatic way into a much more manageable form of profiling data, essentially, which you can visualize in the viewer, which gives you the most important information, like which type of problem is it, where in your source code is the problem, and which process or thread is responsible for the problem. Now, what's very interesting, I think, is those tools are all interoperable. So first of all, each of the tools which I presented supports PAPI to get the hardware counter data. Secondly, a scenario which you could use is, for example, you start your profiling your OpenMP application with ompp, and you get an initial profiling report. So what you can then do is you can visualize your profiles actually with the paraprof view of tau, and you can also investigate in more detail with tracing with KOJAK and SCALASCA what might be the problem if you're of a problem which you have identified with ompp. And in both approaches, both tau and KOJAK do tracing, and what you can actually do is you can take the traces which you generate by KOJAK and SCALASCA or by tau and visualize those traces even for OpenMP in Vampire. And Vampire then allows you to see in very detailed way what's going on in your OpenMP execution. So I'm at the conclusion. The vendor tools are usually very powerful and well supported, and you have the advantage that you have an integrated single solution. The tools from academia have the advantage that they are mostly platform independent, and I'd say in some sense they can be actually technologically more advanced. For example, SCALASCA supports scalability to several tens of thousand processors. Another thing is many tools in the academic world have tried to explore automation to support the performance analysis process. Often those tools are also interoperable, but the technologies which are used by vendor tools and tools from academia are actually often orthogonal. So many vendor tools use statistical sampling, while in the academic world, measurements are usually used to get the data. And with that, I thank you for your attention. I'm glad to